Hello and welcome to this video, which is part of OCR A-Level Physics, looking at Module 4, Electrons, Waves and Photons, looking at the topic of waves and looking at our concept of progressive waves. So if we've been successful and we've learned in today's lesson, we should be able to define a wave as an oscillation of particles in a medium, understand and describe a longitudinal and transverse wave, deduce the different properties of waves. So in this lesson we're going to be looking at the following parts of the OCR A-Level Physics specification. 4.4.1 Wave motion. Now there are many different types of waves, but what is a wave? Now wave behaviour is common in all systems, and waves carry energy from one place to another and can also carry information. Now waves do this without transferring matter with the energy, so a wave which does this is called a progressive wave. So we can consider waves to have the following shape. Now you can use waves in many different real-world applications, such as mobile phones or listen to the radio. Now designing comfortable and safe structures such as bridges, houses and music performance halls requires an understanding of mechanical waves, whilst modern technologies such as imaging and communication systems can show how we can make the most of electromagnetic waves. Now from that particular diagram of a wave, we will consider the following on the screen to be one wave. But what is the definition of a wave and what are the different types of waves? So a progressive wave is a mechanism that transfers energy and or information from one place to another without the net movement of matter. So for example, the energy can start at one place, travel along in a direction and finish at another place, but the particles do not travel at all during this. So you can see in this particular animation with the wave actually moving, you can see how the energy is transferring but the waves are not. So what will happen is the particles will vibrate or oscillate backwards and forwards, but there's no net movement of the particles. But they will transfer the energy between each other, allowing the energy to be transferred in the wave. Now in a progressive wave, energy is transferred but matter is not, and we can see this in a number of examples. So for example, when a twig is dropped into a calm pool of water, ripples form on the water's surface. The ripples do not carry the twig or water away with them, though. If you strum a guitar string and create sound waves, the sound waves do not carry the air away from the guitar and create a vacuum. When you speak, your voice box vibrates, making sound waves that travel through the air, but the air itself does not travel away with your throat, otherwise it will create a vacuum. So in your progressive waves, the waves will cause the particles to move backwards and forwards as shown in the following animation. So it could be in the horizontal plane or it could be in the vertical plane, that the wave will cause the particles to move backwards and forwards. Now this backwards and forwards motion is called an oscillation or a vibration. So a wave causes particles to oscillate or vibrate. Now one complete wave or oscillation is when the particles move one way and then the other way and go back to where they start. This cycle, shown on the screen, is one complete oscillation or wave. Now, when a progressive wave travels through a medium like air or water, the particles in the medium move from their original equilibrium position to a new position. The particles in the medium will exert forces on each other. A displaced particle experiences a restoring force from its neighbours and it is pulled back to its original position. Now in addition, collisions between particles in the wave can also provide the restoring force to bring it back to the equilibrium position. Now the correct name for energy transfer in this context is called propagation. Now the way in which the particles vibrate allow you to classify the waves, and what the wave vibrates and what is vibrating in the wave allows you to classify the waves. So just to clarify, a wave can be an oscillation or vibration of particles. The oscillation is the representation of the energy found in the wave. The greater the energy in the wave, the larger the oscillation. Now there are two different materials which can be oscillated by a wave, which gives us electromagnetic and mechanical waves. So a mechanical wave is a wave which has oscillations of matter, for example atoms. So a mechanical wave is caused by particles vibrating at a source. Now in this animation there is no displacement of particles. the particles are moving backwards and forwards. Now this means that for mechanical waves you need particles for the energy to be transferred. Mechanical waves cannot travel in a vacuum. And remember, there is no net displacement of particles, so we state there is no overall movement of particles. So for example, in a sound wave, the particles do not travel from the object making the sound, the human mouth, to the object detecting the sound, the human ear. The sound wave is a series of particles vibrating backwards and forwards, colliding with the next particle and making that particle vibrate, passing the energy on. Now particles will oscillate or vibrate in the substance and pass energy onto the neighbouring particles. Now this means mechanical waves need particles to be transferred, so mechanical waves will not travel in a vacuum, such as the vacuum of space. Now an electromagnetic wave is an oscillation of the electromagnetic field lines. So an electromagnetic wave is caused by the fields oscillating at a source. So this means that electromagnetic waves do not need particles to travel. They only need the electromagnetic fields which permeate the entire universe. They can travel anywhere, even a vacuum. So for example, electromagnetic waves can travel over the vacuum of space. Now electromagnetic waves in a vacuum can travel at the fastest possible speed in the universe. The speed is 3 times 10 to the 8 meters per second, and nothing can travel faster than this speed. So electromagnetic waves travel faster in a vacuum as there's no particles present to slow these waves down. So electromagnetic waves are oscillations of the electromagnetic field. They can travel through a vacuum. All electromagnetic waves travel at the same speed, the fastest speed in the universe, 3 times 10 to the 8 meters per second, commonly called the speed of light in a vacuum. Examples of electromagnetic waves include light, infrared, gamma and radio. Mechanical waves are oscillations of particles. They cannot travel through a vacuum. Mechanical waves travel at different speeds depending on the material they are travelling in. Examples include sound waves, water waves, seismic or earthquake waves, and waves on a string. Now waves can oscillate in 2 ways, giving 2 different categories of waves, either transverse waves or longitudinal waves. Now in longitudinal waves, the oscillations are in the same direction as the energy transfer. In transverse waves, the oscillations are at right angles to the energy transfer. So, with transverse waves, the oscillations of a transverse wave are perpendicular to the direction in which the wave propagates. Now, in a wave, the particles do not move position, they will only move backwards and forwards or oscillate. So, for example, here's an example of a transverse wave oscillating, a water wave ripple. Now, longitudinal waves are ones where the oscillations are parallel to the direction in which the waves transfer energy or propagate. So once again, in these waves, the particles do not move position. They only move backwards and forwards or oscillate. So to clarify, the oscillations of a transverse wave are perpendicular to the direction in which the waves transfer energy. If we assume the energy propagates from left to right, the waves oscillate up and down. All electromagnetic waves are transverse. For example, radio, light, UV, X-ray. Longitudinal waves have oscillations which are parallel to the direction in which the wave transfers energy. If we assume the energy propagates from left to right, the waves oscillate from left to right. Examples include sound waves, seismic waves, and water waves. So we can see in this diagram the difference between transverse waves and longitudinal waves. Now, transverse waves have peaks and troughs where the oscillating particles are at a maximum displacement from their equilibrium position. Now, in a longitudinal wave, when they travel through a medium, they create a series of compressions and rarefactions. So we can see these 2 concepts in the following 2 particle images of transverse waves and longitudinal waves. Now here is a diagram of a transverse wave. We can describe the transfer of energy with lots of different terms to detail wave motion. So we can see here that in our transverse wave, the particles do not change position. They will only move backwards and forwards. They will vibrate as they travel along this wave motion. Now the first type of concept we've got to understand is amplitude. Amplitude is measured in meters, and the amplitude of a wave is the maximum displacement of the particles from the equilibrium position. The equilibrium position, as you can see on the screen, and the equilibrium position is the rest position of the particles or the field lines. Now the wavelength is measured in meters, and the wavelength of a wave is the length of one whole cycle. It can be measured as the distance between two peaks. It is the distance travelled before the wave repeats itself. The time period is measured in seconds, and this is the time for one complete wave to happen. Like wavelength, it is measured as the time it takes between two peaks. Frequency is measured in hertz, and is the number of complete oscillations of a wave in 1 second, and this is closely linked to the time period of a wave, as frequency is equal to 1 over time period. So to recap, amplitude is measured in meters, and the amplitude of the wave is the maximum displacement of the particles from the equilibrium position. Wavelength is measured in meters, and the wavelength of a wave is the length of one whole cycle. It can be measured between two adjacent peaks, troughs, or any points on a wave, and the same point one wave later. The time period is measured in seconds. This is the time taken for one complete wave to happen. Like the wavelength, it can be measured as the time it takes between two adjacent peaks, troughs, or to get back to the same point on the wave. Frequency is measured in hertz, and the frequency of a wave is the number of waves passing through a fixed point every second. Wave speed is measured in meters per second, and the wave speed of a wave is the distance travelled by each wave every second. It is the speed at which energy is transferred by a wave. Now this relates the frequency in hertz, the wavelength in meters, and the wave speed in meters per second in our wave equation. So the wave speed is equal to frequency times by wavelength, or V is equal to f lambda. So if a wave has a frequency of 5 Hz, each second there are 5 complete oscillations. If each wave has a wavelength of 2 meters, then the wave must have travelled 10 meters from the source in that time. Therefore, its speed must be 10 meters per second. Now, a graph showing the displacement of the particles in a wave against the distance along the wave is sometimes called the wave profile. This can be considered the snapshot of the wave. Now, the wave profile can be used to determine the wavelength and amplitude of both types of wave, as the displacement of the particles in the wave is continuously changing, so our wave profile changes shape over time. Here are images of the wave profile of transverse waves and longitudinal waves, which you can see here in a bit more detail on the following graphs. Now, if we look at the wave profile for either a transverse or longitudinal wave, you can see how the particles here, labelled P, Q and R, oscillate from equilibrium to a maximum positive displacement to equilibrium, to a maximum negative displacement to equilibrium in a cycle. Now the particles do not move with the wave, they only oscillate. Now you can determine the new position of a particle as the wave pattern will travel through the particles. In this case, the wave pattern is travelling from right to left. So in that instance, my apologies, it's going to be travelling from left to right on the screen. My apologies for you for that. So therefore the particle will go to the position of what the particle was immediately to the left of it beforehand. So you can see that in the following images. So as it's travelling from the screen from left to right, you can see the wave pattern is travelling through the particles, and you can predict what the position of the particles will be. Now the frequency is one of the most measurable properties of a wave. Frequency is linked to the time period of the wave and the wavelength of the wave. You must be able to calculate frequency. Now remember, frequency is how many waves are produced or pass a point every second. So the frequency is the number of waves produced by a source each second, or the number of waves that pass a point each second. The unit of frequency is hertz, so 1 hertz is 1 wave produced per second. 20 Hz is 20 waves passing a point per second. Frequency is calculated with the equation of frequency in Hz is equal to 1 over time period in seconds. So a wave has a time period of 4 seconds. What is the frequency of the wave? So we say f is equal to 1 over t. So f is equal to 1 over 4. So f is equal to 0.25 Hz. Always check your answers are given with the correct units and to the correct significant figures. Now, a cathode ray oscilloscope, or CRO, is a laboratory instrument used to display, measure, and analyze waveforms of electrical circuits. An oscilloscope can be used to determine the frequency of a wave. For example, using a microphone, we can produce a trace on the screen. Now, the oscilloscope screen will show the potential difference or voltage on the y-axis, or the Y gain, and the time on the x-axis, or X gain. Now, each vertical square on the screen can be set to represent a value of potential difference. This is called the Y gain. So if the Y gain is 10 volts per centimetre and each square is normally 1 centimetre in height, then each square represents 10 volts. Each horizontal square of the screen can be set to represent a value of time. This is called the X gain, or time base. So if the time base is 1 millisecond per centimetre and each square is normally 1 centimetre in width, then each square represents 1 millisecond. So if we measure the time period of the wave from the oscilloscope screen, then the frequency of the wave can be determined by the equation F equals 1 over t. Now, to gain accurate results, the Y gain and time base should be altered so that a full waveform is on the screen. And to gain accurate results, the trace should be moved so that the key positions align with the squares on the screen, so that it's easier to measure accurately. So if the Y gain was 4 volts per centimetre squared, and the X gain was 2 milliseconds per centimetre squared, one full time period you can see on the screen as 2 squares, so it means it's 4 milliseconds. We know F is 1 over t, so F is 1 over 4 times 10 to the minus 3, so it equals 250 Hertz. So to summarise what we've looked at in today's lesson, we looked at the idea of progressive waves, longitudinal and transverse waves, displacement, amplitude, wavelength, period, frequency and speed of a wave, techniques and procedures used to use an oscilloscope to determine frequency, the equation F equals 1 over t, the wave equation V equals F lambda, and graphical representations of transverse and longitudinal waves. So if we've been successful and we've learned in today's lesson, we can define a wave as an oscillation of particles in a medium, understand and describe a longitudinal and transverse wave, and deduce the different properties of waves. So thank you for watching this video on OCR A-Level Physics, Module 4, Electrons, Waves and Photons, in the topic of waves and the concept of progressive waves. Thank you so much and have a lovely day.